Great. Chapter 5, Backtracking. Okay. As always, we'll start with a nice quote. I like this quote by Robert Frost, author and commentator and things like that. I'm not a teacher, but an awakener. We'll essentially be talking about backtracking algorithms, as I mentioned, right? Here is the syllabus for backtracking. Right? We'll figure out what backtracking is, the general method of backtracking. Today we'll definitely get into the n queens problem. There are other problems that are discussed as part of this backtracking slide deck are sum of subsets. I'll tell you what those are, and then we have the graph coloring where this is used, and then we get into Hamiltonian cycles. Okay, so we are in the home stretch now. Over the next couple of weeks, we'll spend about a week on Unit 5, another week on Unit 6, and then whatever remaining classes are there, there could be a little bit of spillover into the next after the 2 weeks, and then we'll do the review of all the modules for your final exam. So that is the plan of action. Okay, without wasting any time, there's a group exercise for the next 20 minutes, 15 to 20 minutes. Okay, this is what I want the class to do. Participants, somebody is, hold on. Somebody has, can you mute yourself, please? Or is not on. Kaushik, are you on mute? Okay. ASET, are you on? Okay. Somebody, 205736, I muted them. Okay. I think all of you are on mute. Kate, woman. Okay. I did not start my video. I'll start it on later. So faculty members facilitate the exercise. What I want you to do is the following. Take groups of 2, right? Take a sheet of paper, draw a 4x4 table, okay? And then your goal is to put the 4 queens, okay, such that no queen can take the other queen, right? So no 2 of them are in the same row, column, or diagonal. Okay. Now, it's easy to place them, but what I want you to do is, right, don't do it yet. Follow the instructions first. Okay. I want you to write down your thought process as to what you are doing there. Let's say you place your queen on cell 1-1. Okay. Then the second queen goes somewhere. Okay. Now, in the process of doing that, what are all the things that you are doing? You have to document. Okay? And then we'll discuss what you do. Now, there's a second problem that I filled out here. That is a queen's problem. Second problem, by the way, if you finish the 4 queens, try doing 8 queens too. Okay? If you finish the 4 queens problem in 2 minutes, because you're a smart aleck, you play chess, you know how to do it, right? Then you try to make an 8x8 grid and try to place 8 queens. Do it with a pencil because you will do some erasing. I can tell you that. Okay? And there's a second problem that I gave you there, saying that find out all 3-bit binary numbers for which the sum of the ones is greater than or equal to 2. You know binary numbers, right? You're computer science students. I'm talking about 3-bit binary numbers. Okay? I'm not giving out the full story there. So I want you to find out, mark all the 3-bit binary numbers where the number of ones is greater than or equal to 2. Okay? These are the two exercises to begin this chapter on backtracking. Okay? Again, document your thought process. If you are done with your 4 queens problem quickly, then tackle the 8 queens problem, meaning it's an 8x8 chessboard, and then you try to place 8 queens such that no 2 queens are in the same row, column, or diagonal. Okay, I can tell you 8 queens problem to put it on a chessboard is a tougher exercise. Okay, start with 4 by 4, then move on to 8 by 8. Okay, after you're done with the queens problem, you can do the 3-bit binary numbers. Faculty members, please facilitate for the next 15 to 20 minutes. Ready, set, go. Process, what I would do, I would say step 1, I'll place my queen. Where would I place it on an empty, nice whiteboard? Since I think in a structured way, left to right, top to bottom, very likely I place my first queen on row 1-1, cell 1-1. Okay. So I cannot place the second queen as a rule in the same row and in the same column. So step 2. Step 2, what I'll do, I'll increment the row count. Right? So because I cannot place it in the row, right? I'll increment the row count, step 2. So now I'm row 2. Okay? In row 2, I cannot, the rule says I cannot place it in column 1 because my row 1-1, I already have something. Correct? So that means I should keep track of somewhere, I should keep track of some array where I am placing the queen, the index, right? So that way you see the next empty slot where there is no clash between the row, column, and diagonal. So that means by applying that rule, I will place the queen 2 on row 2 and column 3. Correct? Somebody put 1-1 and 2-3, I think. Let me check. I'm hiding, part of the screen is hidden, but yeah. So there you go. Somebody is explaining, right? Trace back to the previous level, okay? 2-3. Got it? Okay. Let me continue the thought process and see if it works, okay? So somebody keep track of it. I have written 1-1 and 2-3. Okay, now what do? Now I go to row 3. Okay, I cannot place in column 1. Can I place it in column 2? I can, right? Because there is nothing, there is a diagonal or column, there is nothing there. So I place my third queen in 3-2. Okay. Now when I want to place the fourth queen, where can I place? Can I place it in 4-1? You can answer the question. Can I place it in 4-1? The answer is no, because remember I placed a queen in column 1. So 4th row, column 1, I cannot place. Can I place it in 4-2? No, I cannot because I placed the queen in 3-2 earlier. Okay. Can I place it in column 3? I cannot because I placed the queen in 2-3. Okay. Can I place it in 4, row 4-4? I cannot because it is diagonally opposite row 1-1. Got it? So now what do? As DMS has said here, they put it in for all, yeah. So you have to trace back to the previous level. The tracing back is the essence of backtracking. That means we're tracking back. Okay? So now after you track back, then you have to again readjust the pieces. Right? So recursively you track back. Somewhere here they said they use recursion and all that. Yes. Ultimately you implement it as a recursive solution, but this is how you do it. So in simple ways, you keep placing it, and if you reach what is known as a dead end, meaning you cannot go any further, then you backtrack to the previous level and try. If it doesn't work there, you backtrack to the previous level and try. Like that, you recursively backtrack to all the levels and try. And if you cannot still achieve it, then there is no solution. Okay. Has anyone attempted the 8 queens problem? Did anyone succeed in placing 8 queens on the board? I see Kite guessed on a cell phone. I don't know whether she's on cell phone or not. I see a student holding something to her ear and Kite. Can Kite guest hear me? Is there a faculty coordinator in the Kite guest in the room? The total number of ones in that number is greater than or equal to 2. You got it right? You can just put the answer for everyone, or I can just copy paste it. So you had to list down everything to figure out. That's another variation of backtracking. It's like when you're building the solution, there'll be some backtracking. But since it was just 3-bit binary numbers, 2 raised to 3 is, you have 8 numbers, right? So 0, 0, 0, 0, 0, 1, like that, 8. So out of that, you could clearly see that 1, 1, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 1 have more than, greater than or equal to 2 ones, okay? This is just to give you a taste of what kind of things you do in backtracking, these 2 exercises, okay? Perfect, 6, 3, 5, 7, okay? Excellent. Okay, now let's proceed with the class. Okay, let me take out this one here. Okay, so welcome back all. We missed one class because of my family obligation that came up in the last minute, last Sunday, I believe. And then, of course, the following Thursday when I logged in, none of you were there. Turns out it was Shivaratri holiday for you. I hope you all had a great Shivaratri break. We're in the home stretch here, so let's proceed. So what is backtracking? Backtracking is a technique used to solve problems with a large search space. As an exercise, I gave you a small search space. Okay. So you're trying to solve them with a large search space, and then as you are trying to solve it, you are eliminating the possibilities. That is what you have done with your 4 queens problem, correct? Okay. The other interesting thing would be is backtracking would be to solve the maze problem. You know, in computer programming, this is something that we all computer students do, right? We write a program to do a maze. Everyone knows. Huh? And the student has sent me a note. Very nice of you. What's your name? She had to take the call because it was coming from IIT Bombay regarding a summer internship online exam. Okay. fair enough reason. Okay, so that's good. It's an important call. So all you have to do is when you're taking the call, you can just walk out of the classroom. So that way, the rest of the students are not disturbed. That's all you have to do. Okay, so you're excused, no problem. You can continue in the class. Okay. We do all get calls. Like for example, when I'm teaching, I get a lot of interruptions, right? I can get a call from my wife, my kid, my students know that, hey, if it is coming from any of my family members, I take the call, as simple as that. Except as an instructor, I don't leave the classroom. As a student, you have to. So that way you're not disturbing anyone else, okay? Okay. Everything is forgiven, forgotten. Let's proceed. Okay, so let's talk about the maze problem here. See, by the way, I do it very impartially. Last week, remember, last class we did, if you recall, one particular college, I don't know which one, we told them so many times to be on mute and don't unmute yourself. They unmuted and I had to simply expel them from the class. Because those types of distractions would be detrimental, at least to me. Okay, going back here. So you have a maze. So what is a maze? Everyone knows, right? Maze, you have a starting point and you enter one way and then you exit some other way. Okay, in between you have this big maze in the center. So you take some paths, you get stuck. Then what do you do in a maze? You come back. And then you try another branch. Okay, if you get stuck, you again backtrack. Try another branch. That's how you make progress till you exit from the other end. That's what the maze is, right? A pretty standard example of backtracking. Okay, so yeah. So you can see here you have two paths here called portion A and portion B. Okay, so different ways, right? So from that particular starting point called a junction, right? Because you have two paths. When you say junction means it's like a decision point. You go left, you go right, or north, south, whatever the directions may tell you, right? So if you get stuck, then you backtrack to the junction. So that means some junction you're keeping track of. There can be many junctions in problem space, right? Okay. So when you're backtracking there, you know that portion A will not lead you out of the maze. So then you try portion B. Okay. Now, obviously, in this example, we showed you two paths, but you could have more than two paths. So you have to try out each of those paths. Okay. You can see there's another junction here. He's showing an illustration where you have 1, 2, 3 paths. Technically, 3, yeah. Actually, more. He's showing the other paths too. Yeah, A, B, and C. You're showing 3 paths, and then the strategy basically says you try each choice one after other. That's what it means. Okay? And then if you get stuck, backtrack to the junction and try the next choice. Okay? Concept is very simple, right? Backtracking, you have choices to make to reach your destination. You try out each of those choices. If it allows you to reach the destination, you're good. But if you try all of them and you found no way out, then there is no solution to the maze. Okay. This is the illustration of that, right? You have a starting point on the left, and then you have to reach somewhere. As a slide, it is already showing which path leads you to success, right? But you can see here, as I'm building the thing there, there's only one way out for success. At every point, you're branching out, and if you reach a dead end, you're backtracking. There's a back arrow which is showing. Okay. So if you notice one thing here, does this look like a tree to you? It is, right? Starting point is a root node, right? And then you're branching off to the next level. Then you're branching off again to the next level and so on. So whenever we talk about backtracking, you will utilize the concepts of tree and the tree traversal to come up with a solution. Okay? Now we cover trees, right? So some terminology, since we are talking about trees here, this one you already know the terminology, so I'll just breeze through it, right? So in this case, we are talking about three kinds of nodes here. Root node, that is the green one, right? That is your starting point. Okay, then you have these internal nodes. And then you have the leaf nodes. Okay, so your goal is to say, hey, when I am transposing the problem space into a tree structure here, if I can reach a path where one of the nodes leads to the exit or the goal, then you're good. Okay, so we transpose the problem into saying that, hey, I'm searching for a tree for a particular goal leaf node. So one of those red nodes, leaf nodes, is a success. Okay, just like how we had it here, right? When you go back to the previous slide, see that ultimately one node led to success. Okay. So each of the non-leaf nodes is a parent of one or more other nodes. Okay, we know that, right? Parent and child relationship. Okay, and each node in the tree other than the root has exactly one parent. Okay? The moment you have two parents, you will get a network. It's no longer a tree. Okay. Okay, that's all pretty. You understand this? I don't even need to explain that. Okay. Now, in data structures, we talk about trees, right? As such, as we did earlier too. But here, we are visualizing. We are using the concept of a tree to visualize the sequence of choices. Okay. So that is what we are doing. So we are understanding the problem space in terms of a tree structure to arrive at the solution. So here is a back algorithm. Remember, I asked you to write down your thought process, right? So you can match your thought process, excuse me, to what is listed here. Okay. We explore each node. Okay. We start with the first node. Okay. If that is the goal node, then you return the success, meaning you reach the goal. But if it's a leaf node, then you return failure. Okay. For each child C of n, meaning for every children of that, let's say the n is the root initially. It has let's say it has 2, 3, 4 children. Ultimately, I'll tell you that we usually do it by representing it as a binary tree. That means you have 2 branches. Okay. And then you explore each of those children. And if any of those things is successful, you return success, otherwise you return failure. So the algorithm is a fairly straightforward algorithm. Now, how do you convert that into a piece of code is what we will see here. Okay. Very soon, you will trace code. Remember, by now you know the modus operandi, right? Whenever we need to code, I give you code and say, okay, take the small problem space and then trace the code. So that's how you gain insights. It's learned by doing concept, right? But if I explain you the code and you're staring at it, you would not learn. By the way, I would not learn staring at the code. I have to do it. I have to trace it. Okay. So let's look at the 8 queens problem. Okay. So what we do is we construct the state space tree. That's basically the tree that I have shown you. Okay. So in your four queens problem, you were in essence maintaining that. Okay, but how subconsciously you are maintaining that. But I'll show you how you do it visually also in a few seconds. Okay? So when you are building that state space tree, all the nodes represent the partial solutions. Okay, and then the edges show the branches, like which choices you are making. Okay, typically in backtracking, you use the concept of depth first search because one of the leaf nodes is the success, right? So you want to go deep. Okay? Now, when you want to start optimizing the branching thing, you start pruning the tree instead of building the full tree, because if you have to build a full tree, it is going to be humongous, right? So when you're optimizing it, you prune, meaning any non-promising nodes, you mark them. Okay, so that way you don't have to go further than that, beyond the non-promising nodes. So it's called pruning. So we'll take a look at how that looks too. Okay. So you have seen this one earlier. So I have a couple of duplicate slides here. I did not remove them, but I'll show you the state space tree for the four queens problem. So how do we interpret the state space tree here? It's actually a legitimate question, by the way. I do not know if in India they can ask you. I can give the four queens problem like how I gave in the beginning and ask you to draw this diagram. Okay. So you see very at the top, right, at the root, it's an empty chessboard. Okay. So then you put the queen in, if you see left side, I'm following the left side, branch 1. Okay. Remember we said we put the queen in cell A11 or 1-1 cell, right? Okay. Now once you put the queen there, then what are you doing? You're branching, you're going depth first, right? So that's why you have choices. You have 1-1, you put it, 1-2, right? Like that you build the tree. If you go down there, you can see you're taking the branch 2. Okay. So when you take the branch 2, row 2 rather, not branch 2, row 2, right? Because you have row 2, 3, right? So you go to row 2 and then you can see the queen there, row 2, column 3. Okay. So you build a tree like that all the way, depth. Once you have the state space tree, ultimately you do some backtracking, you see the dotted lines and all that, right? Ultimately backtrack and you can see a solution on the right, ultimately where you got it. That queen placed in 3-1, 3-1, 1-2, 3-3, and 2-4. Okay. So you're applying, you're building, you're visualizing the problem space like a tree. You're somehow keeping track of where you kept them, right? Ultimately, one leaf leads to a solution for that. Okay. Now, 8 queens is making arrangement for 8 queens on a single chessboard. Okay. You all know how to, I don't have to teach. I think pretty much every Indian knows how to play chess now, right? Note the restriction here, right? Due to the first, these restrictions, we know that you can only place 1 queen in any given row column, right? So each row and column of the board will have exactly 1 queen, okay? So here is a solution, by the way, for the 8 queens problem. I asked you to try 8 queens, right? In case you finish 4 queens, I do not know if any one of you were able to solve that problem. Not an easy problem to solve. I forgot how many solutions are there. It was the number of solutions, about 8, to place 8 queens on a chessboard is some 30,000 or something like that solutions. I have to, if somebody can Google up and tell me, I forgot how many solutions are there. So how does it work? This shows you the example, right? Place a queen on the first available square in row 1. That's 1, 1, right? Move to the next row. Place a queen on the first available square there. Okay? That doesn't conflict with the previously placed queens. That's exactly what I explained when you did the exercise, right? Okay? Continue in this fashion until you two conditions, right? You have solved the problem or you get stuck. Okay? Okay? Then when you're backtracking, what are you doing? That is point B there, right? Remove the queen that got you there until you get to a row where there's another valid square to try. So that means what? In the 4 queens one, the third one that I placed, I will remove it, right? And then like that, I backtrack to the second row. Okay, and then of course ultimately the first row. Okay. I didn't know that I have animation here. I forgot. Yeah, see, it put it there. What happened there? It was there. You placed 5 queens. Now you want to place the next one. You're not able to place it, so you took that one out. And then just the previous row. Okay, let me show you one more time what is happening. Okay, first queen. Okay, I'm applying corresponding to the steps on the left, right? Second queen. Place on the first available square. Everyone understands that, right? Third one, available square, right? Placing, I'm in step 2. Okay, that doesn't conflict the previous queen's placed. So far, so good, right? Place the next one. Okay, so far, so good. Then that one too. So we're able to place 5 properly. Now I want to place the 6th queen. So I cannot place it in column 1, column 2, column 3, column 4, column 5. I cannot place it in column 6 either because 1, 1 is diagonally opposite that, correct? Can I place it in column 1, 2, 3, 4, 5, 6? No, because 5 clashes with 1, 1, 6 clashes with 2, 3. Right? So I cannot place it. Now, can I place it in 7? No, I cannot place it because it clashes with 3 and 5. Row 3, column 5. And I cannot place it in column 8 because it clashes with row 5. No, row 3, column 5. Yeah. So I cannot place it anywhere. So that is subsection B there, right? You get stuck. So what are you doing when you're getting stuck? You remove the queen that got you there until you get to a row where there's another valid square to try. Valid square. So what is the last queen that we put? That is here. That is 1, 2, 3, 4, 5. Row 5, column 4 is the last queen. Correct? So I need to put it into some other square. That's what this says, right? Okay. So I move that queen to the next valid square. Okay. Now you try to place the queen in the 6th row. Okay. Let me pause here. Any questions, comments? Do you understand the concept? Anyone has questions? Put it in the chat. Okay, we did the 4 queens, right? Now remember, one of the people in the chat, they talked about when I asked them to explain the 4 queens, they said they use recursion. Okay. Typically, this is done through recursion, but you can always do it without recursion too. Okay. The reason why you want to do recursion is, right, remember we talked about stack and how all the recursive calls are stacked up in a stack. the system maintains the calling points and all that to the pointers. Okay, so it takes care of it. That's what it says. Okay, so what I have here is a piece of code that solves, not giving a break yet. Okay, I'm just showing you the code. Again, we have to trace the code, right, to understand the logic, but we'll get there. This is kind of hiding the thing there. Let me make it here. Can you see it better now? So I gave you the thing here. There's a perm array. There's a location. Okay, perm is the permutations. And then you say what are all the used squares. Okay, squares meaning in this case rows, right, which have been used. So it is keeping track of that. And then obviously you can see if there's some logic involved here. Unless you trace it physically, you will not understand the logic. Okay, so there are comments there. I'll make you trace it after I'm done with the lecture. Okay. Yeah. So if you do the brute force approach for 8 queens problem, you can see how many permutations are there. Remember, you did the problem 2, right? Binary numbers with three binary number stuff that we did. There were 8 combinations. It was easiest to list the 8 combinations and figure out those 3 or 4 that had more than 2 ones. 2 or more ones, greater than or equal to 2, right? But you can see if you do the brute force on 8 queens problem, the combination is 40,320. Okay? Pretty exhaustive search, right? But if you do the backtracking one, it is shown that basically you will reduce that 40,322, okay, to 15,720 possible queen placements. Okay, it reduced the space by what? Almost like 40-15, right? It's almost like 1/3, little over, yeah, let's call it 1/3. Significant saving, right? But when you apply some pruning techniques, you can further reduce it to 5,508 possible queen placements. Okay, so that's how the scientists used to do, right? These kinds of problems, they were always trying to see what is a small optimization that can do. Start with brute force, apply some certain optimization principles, and you brought it down to what here? From 40,320 to 5,508. Okay, pretty interesting statistic there, by the way. Let me go here. Okay, let me stop here. Questions, comments? Okay, so let me continue with the lecture. I'll give the assignment at the end, okay, to work on. Then in the backtracking slide deck, we have this thing called coloring problem. Okay, let me ask students a question. You all have seen maps, right? Globes, map of the world, map of India, and all of those things. It's a no-brainer, right? Did anyone ever pause to think how many colors are used to color the map? Faculty members don't answer. Let the students answer. Let's take India map. How many colors are used in an India map? Do you know? Anyone knows what that number is? How many colors are used to show all the states of India? There are maximum 50 states. Is it 50 or no, why am I saying 50? Sorry. 50 is in US, right? In India, how many states do we have now? 30? I remember when it was 25, but we keep splitting, right? With the latest addition of Andhra and Telangana, How many states do we have now? 30, 32, whatever, right? Do you know how many? So do you think we need to use that many colors to color the map? What is the use? What is the purpose of coloring a map? What does color give you when you are doing coloring for a map? What is color providing you? Can somebody tell me that? Students, don't feel shy. Answer. No answers are incorrect. It's all learning, right? What does the color signify? Is there any meaning to color? I'm expecting some answer. Faculty members are welcome to answer too. Students will get your perspective nicely, as opposed to listening to me only. So the question is, we have a map. Talk about India map. How many colors are used in the India map? That's one part. The other part is, what does color really represent in a map? Why do we use color in a map? Very interesting problem. This coloring problem is a classic problem, by the way, in graph theory. Okay, looks like nobody wants to answer. I will answer, okay? So, give me a second. Before I answer, let me take my 2-minute break now. 2-minute stretch break. We'll come back. More than clumsiness, it's really about demarcation, right? So the example I was giving was like, let's say Andhra and Telangana. Or maybe Andhra is colored yellow in the map. And then adjoining Andhra, you have Telangana. Obviously, you want to use another color to distinguish all this boundary. It's kind of like boundaries, right? It demarcates between the various locations or states in this case. Okay, that is one of the reasons why we use the coloring problem, right? Different colors denote different things. There are a lot of practical applications for that, right? When you are doing the what they call it as like teams, for example, team names. Names are another aspect of color, right? Like if you go on a field, when cricket teams are playing, you see the cricket teams have different colors, right? They both will not wear the same color. And it will become very hard for the spectators to distinguish between the two teams, right? Same thing like in a football field. So this color, the application of color is a universal thing. Now, mathematicians have nothing better to do than to beat these problems to death, right? Then somebody said, I'm saying it in a good way, guys. If there are any professors there with mathematics background, don't take it personally. I'm just saying it in a light-hearted way there. As one professor here in US said, we can blame all of our computer science problems on mathematicians. Okay? So going back to that. So then they decided, okay, now if I have a map, if I have 50 states in the case of US, how many colors do I need to use to represent all the states without any confusion? Right? The map has to show clear demarcation of the boundaries, right? Same thing, if it's a world map, how many colors do I have to use? Okay. Do you think the number of colors that I need to use to show a world map would be greater than the number of colors that I need to use to show, let's say, an India map? The question is, do you think that I have to use more number of colors on a world map as opposed to showing an India map? Yes or no? Yes, somebody said yes. Okay, I know you can put it for everyone, don't worry. 205,736. I get the feeling I'm talking to a robot when I see an IP. It's almost like an IP address. 205,736,546. It is an IP address, yeah. The answer from there was, yeah, you have to use more colors to show clearly all the distinctions in a world map as opposed to India map. Now, I'm going to give you the answer. Actually, no. The maximum of colors that you need to show any of these things in a map problem is only 4. With 4 colors, you can show everything in a map. Just 4 colors. Whether it's India map, world map, it doesn't matter. 4 colors. It's a very classic computer science. It's actually a graph problem, by the way. How many colors you need to show different nodes of a graph and things like that, where no 2 adjacent nodes have the same color. So if each node is representing a state or a country, right? So you can translate that into practical applications like that. It's actually 4, guys. With 4 colors, we can do everything. Oh, okay, let me introduce this. See? That's what this is. So what we'll do is we will, of course, I already gave you the answer, so let's not do the exercise here, okay? Or we can do it visually, right? How many colors do you need to color this graph? No 2 adjacent verses share the same color. Let's say if I say A is blue, okay? Then we'll do it as a group exercise, okay? So I'm saying, I'm putting in the chat. I'm starting with the primary colors, right? What are the primary colors? Primary colors are what? Green, red, and blue, right? We used to remember it very well as students, what the primary colors are, because as GRB, and those were the initials of our professor, G.R. Babu. Very nice man, he passed away. So if I say A is green, okay, then E has to be, because E is adjacent to A, right? So E has to be some other color, right? So I can say E is blue or red, GRB, right? E is red. Okay. Then C has to be another color, right? C is blue. Okay. We are done with that. Now, if C is blue, and E is red, can B be green? It can be, right? Because B is green and its adjacent neighbors are E and C, those 2 are in different colors. Now, if those are 2 different colors, then what can D be? What is the color of D? We can say D is maybe yellow. You see, I need 4 colors here, right? D cannot be blue. Okay. You can see I need 4 colors to represent that, because it cannot have the same color. Okay. Not more than 4 colors, okay. That's what we did, right? So you need to have enough information too, okay? So again, this is a backtracking problem. Okay, why am I talking about this? Because you are given some kind of a map and you need 4 colors, red, yellow, green, and blue. Adjacent countries must be in different colors. okay? And you don't have any information to choose colors. So you make a choice, and that choice leads to another set of choices, right? So if you're given a map like that, you say you start with red, and you start coloring, and suddenly you get stuck. You can't go anywhere, okay? Then you have to change the colors. It's a beautiful exercise, by the way. I'm sure even in India now they are doing it, right? You know how we do coloring in elementary schools, right? Coloring books and all that. We actually give these types of things there. I remember my children doing it. They come home, Papa, we got this map of United States. We have to color. There are 50 colors, 50 states. How can we color with only 4? I said, okay, do it. You will find out, right? It becomes a beautiful family game to do that. Because in the process of doing that, then we get stuck. Then we have to backtrack, right? So it's a very fun exercise, guys. You may want to do that outside of the class, okay? Okay. So you can see many coloring problems can be solved with backtracking. Okay. So remember I talked about the 4 color. So there's a 4 color theorem. Okay. So you can see for some maps it can be fairly difficult to find a legal coloring. That's why we have computers now, right? Okay. What else I have here? So when you're doing it for some kind of countries to show, right? So you have to use some data structures, right? When you want to convert this into an algorithm and a program, then obviously you need to choose the data structures. So here he's talking about choosing an array of colors, right? So if you say country color I, the index is the color of the ith country. So you're naming the countries 1 through I, right? I could be some number. Okay. So then he chooses some other data structure. By the way, you don't have to understand it right today. We'll go over these things over the next week or so again with some examples, right? I'm just introducing you to these things right now. Okay. So if you have an adjacent countries, he is using map ij to show the jth country adjacent to country I. He's giving the definition of how to read a map. Okay. So the example of map 5.3 means the third country adjacent to country 5. Okay. Meaning it's the country 8. So that means what? The country 5, okay, has at least 3, because the index 3 is third country, meaning there are at least 3 countries which are adjacent. And out of those 3 countries, 1 country is the name country 8. That's how you read that. Okay. So he's basically took that coloring matrix that I gave you, and then he's using some algorithm to create that. So there's some piece of code here, how this is done. We'll go through this again, okay? I'm just introducing you to that one, and I want you to review that before you come to the next class so that way we can discuss it more, okay? You can see setting some initial colors. None of them have any colors to begin with, okay? And then there's a piece of code for that coloring problem. Okay, I gave the full piece of code to do that one. Okay. So what exactly happened in that algorithm is what the recap is. That's what I want you to leave with. Right? So this is a recursive algorithm. And since we are computer scientists, we start with 0, right? Country 0. And at each country, we have to decide a color, what color we'll show for that country. Okay, the rules are that, right? It had to be different from all adjacent countries. And if we could not find a legal color, we report failure. If we could find a color, we use it. And then we recurred with the next country, meaning you go to the next country then. If you run out of all the countries, means you colored them all. Okay, and when we return from the topmost call, because you start from the root, right, we are done. So that is what that piece of code is doing. Okay, let me stop here, at least for today, and ask if you have any questions, comments. What's the time now? 10:52. Okay. So you have kind of like 7 minutes. It's neither here nor there. So let me see what I put here. Give me a second. Do I have any exercise? I don't think I put any exercise here yet. Give me a second. Yeah, I didn't put any exercise, guys, unfortunately. So the class will end early. But anyway, let me end the class with this beautiful quote. I don't know if I gave this quote to you earlier or not. Something happened, my system froze. Oh. Give me a second. There you go. So I want to end the class today with this nice quote. If you're not willing to learn, no one can help you. And if you're determined to learn, no one can stop you. Lovely quote. Okay. Okay, guys. Any questions, comments? I don't have an exercise for you today to give you at the end. I somehow thought I had the piece of code completely. Where did it go? Next class. Or I'll post it in the community and you can trace it before you come to the next class, okay?